Hello everyone. My name is Matteo Pelati, and I'm actually part of DBS Bank, and I'm leading two groups in DBS. One is the Big Data Engineering group, where basically we build the entire big data platform and all the software component on top of it, and the other group is the Global API Engineering, which is recently started, and it's basically an effort to standardize and build a common API layer across the entire bank. So in this presentation, I want to focus on the second part that I mentioned, that is the Global API Engineering, and tell you a little bit about our journey. And the whole purpose is basically to build this common global API layer to be used for any application across the bank. So I guess most of you knows how mobile banking application works. It's usually very, very simple. You have your mobile app or the web app, which talks to a layer which is generally called the experience layer, and this has all the business logic to serve the API for your mobile application. But eventually, this experience layer talks directly to the source system, and source systems are traditionally quite outdated. Like, it can talk to a mainframe system, it can talk to Finacle system, depends on which source system the bank is using, but that's how it works. So, having said that, there are several challenges that any bank is facing when running their mobile banking application, especially when users start to grow and usage of the application start to increase a lot. First of all is obvious scalability and performance. So those systems that were designed like 20 years back, 30 years back, or even more, they're obviously they were not designed to scale up for mobile banking and internet banking. So it's very common to suffer from performance degradation or even unable to log in a large number of users, actually. Obviously, it's very hard to maintain for different reasons. These systems are, as I said, outdated, but the other reason is that different countries and different products, they might be using different systems. So, for example, cards or CASA accounts or loans, they might be using completely different systems. So in one experience layer, you have to basically aggregate all the content from multiple systems. And to complicate it even further, there are different countries, actually. So you might have a system for cards in Singapore and another system for cards in Taiwan. So you can imagine that this translates into making the application more complex because you have to cater for all the differences. And another problem that these systems are typically batch-oriented, and this was okay until some years back, but especially right now where you want to do real-time analytics, you want to do apply machine learning on real-time, that's a problem because your system, your backend system, still relies on batch. So, considering all this fact, we said, okay, we need a much better API layer to be used across the entire bank. We need it fast and scalable, so we need to find a way to get away from this core system, even though it's not easy. Easily queryable, so I don't have to worry about which core system I need to talk with whenever from my experience layer. I should be able to have one single API interface to query for multiple products, multiple countries. That's what I said, country and system agnostic. Easy to extend, so the whole idea is that to have an API layer that is easily pluggable from different groups of the bank. Obviously, as a group, you cannot implement all the API for the entire bank. So the goal that we had was to set up such a layer that standardized the API and make it easy for other groups to deploy API on top of our own platform. Push and pull mechanism, as I said, more and more streaming is coming, so that becomes more important. And having had bad experience from the past, we didn't want to lock ourselves into proprietary technology, so we wanted open source solution. As I said, centralized, because it must be a centralized system, but at the same time, it must self-service and anybody can contribute in building this API. So we started, I'm going to go a little bit faster because the time is so the whole idea is that let's to basically generate events from the source system itself. So what we started doing, we started basically capturing all the state changes event on every source system. We use different technologies to do that. Mainframe, we use Kix event. For database like Oracle, we use CDC. But the whole purpose is to replicate the entire state somewhere else. And all these events, they basically flow into a multiple Kafka topic, and they're handled by one component that we call a projector, which is basically has the role of taking this event and projecting the state of the source system somewhere else. Now, what is this somewhere else? This was one big decision we had to make. We analyzed several databases. Obviously, initially we discarded a relational database because there was no reason to go for a relational database here. And we wanted to use a key value store. We wanted to have a system that was fast for key value lookup, because that's basically what you need in banking. You need key value lookup and you need time series. We wanted open source. We wanted something that was a hybrid solution, flash plus in-memory solution. We wanted it fully distributed and possibly with a shared nothing architecture, because we know the pain of going through of managing a distributed system that is not that doesn't have a shared nothing design. We wanted it to handle pretty complex data structure, not simple key value, but something more than key value. You can think about maps, you can think about lists, and we really want a secondary index, because when you have complex data structure, you need secondary index to be able to index your inner fields. And of course, we wanted it open source, but we wanted some commercial support, because you never know when something can go wrong. So we analyzed four different products. One is Aerospike, the other one is MongoDB, the other one is Redis, and the other one is Apple Foundation DB. Now, initially we discarded MongoDB and Redis for the reason that you see here. MongoDB, we didn't like the architecture because it is not a shared nothing architecture, and specifically for that. And talking about Redis, actually we did several POC with Redis, but the TCO of Redis is very high, because it's not really a hybrid solution. All your data is in memory and is backed on flash, actually. So the best solution we found was actually Aerospike, because it supports everything that we wanted. The other option was FoundationDB, but FoundationDB, first of all, it doesn't have commercial support, and it lacks some functionality that are basically available using the concept of layers of FoundationDB, but that complicates the thing a little bit. So for us, the best choice was Aerospike DB, and that is basically became our cache. Now, the problem, as I described before, we have multiple source systems emitting events, and these events are projected to our Aerospike. Now, these events, the schema of the object coming from the source system might be completely different. Take, for example, a customer. A customer coming from Taiwan, from a source system, might be completely different from the schema of a customer, not completely, but might differ quite a lot from the schema of a customer coming from Singapore. So we needed something more. We needed to have a global model so that when we define a customer, it's a customer, whether it's in Taiwan, whether it's coming from multiple source system, whether it's coming from Singapore. So what we started doing, we started introducing a concept of a normalizer or globalizer. This is basically a rule engine that sits between on the Kafka topic, and the role is basically translating the messages into common schemas. So we basically took all the domains of the bank, and we started saying, okay, let's take a customer for multiple core system and multiple countries, and let's analyze what the common customer object model should be. And this is what we came up with. Basically, we came up with the entire object model of all our banking domains. And for each core system, we basically translate from the source, which it might be binary, might be XML, might be JSON, whatever we want, into a common schema. Now, this is interesting because we said, okay, what are we going to use as a common schema? We considered, okay, this gives you a step further. It tells you, once I project all my data into our database, how am I going to serve this data? Two ways. One way of serving the data is through API. So we have an API layer in front that basically allows you to go and fetch the data from Aerospike. And the second way of serving the data is through streaming. So basically, as a user, you can say, I want to access the current state of the source system, and at the same time, I want to subscribe to all the events that tells me whenever something changes. And these are public API and public topic that anybody can use to develop their application. Now, back to my other question is that we had to define the model. So what do we use for the model? We evaluated several options. We evaluated JSON, we evaluated different options, and at the end, we decided to go with Avro. Avro is a binary representation protocol, actually, and it's especially used in the world of big data, but it's basically also the standard format for Apache Kafka. Whenever you throw a message on a Kafka topic, if you want to make use of all the capabilities of Kafka, like schema validation, etc., schema evolution, etc., you have to stick with Avro. The other thing that we like Avro is not just a serialization protocol, but it also has something on top of it for handling RPC, remote procedure call. Initially, we thought about using protobuf and gRPC. That was also an option, but is not well supported by Kafka as of today. Avro has the advantage of supporting serialization for streaming and RPC definition and RPC implementation. It's compact, as I say, it's binary, and it's even more compact than protobuf actually, and it really supports very well schema evolution, which for us is extremely important. This means that when we release an API, a new version of an API, our customer can still use the old client, and they will never notice actually. Obviously, they will not be able to see the new fields, or they will see the fields as if a data type has changed, they will see the old data type. But the advantage is that we can release new version without requiring our customer to switch to a new version of the client. Okay, so as I said, strongly typed, and we provide directly a library for them. Now, the interesting part is also how do we persist the data? So we have a key value store. So the advantage, you have good and bad things about key value store, but the good thing is that you can pretty much do anything you want, because key value store just gives you, you just provide a key, you just provide a value, and that value can be an arbitrary thing. Actually, it can be a byte string, can be whatever you want, because the key value store doesn't really care. So we tested different things, and then we came up with something that is very, very similar to the record layer, the Apple record layer implementation that they've done for Foundation DB, and how they serve the entire their cloud basically. So what they do and what we do the same. The difference is that they do it in using protobuf, we do it using Avro. But what we do is, if you consider this is an Avro schema, this is actually how the data is stored into the database. So we have a payload field, which is just a Avro binary dump of the value, okay, of the entire object. And then from this binary, we extract some fields. As you can see here, I have customer ID, I have country, which is basically indexed. So we add some additional fields that are used for the indexing. So what we really need is basically the payload, which is the Avro byte stream, and the customer ID or country are just used for indexing purposes. So this gives us the advantage that whenever a user comes in and asks for an API, what we have to do is just retrieve based on a key, read that payload, and stream that payload directly to the client. We don't even care about its content, we don't even care about decoding it. That makes it even faster, because we're basically just reading a bunch of bytes and throwing them on the wire. Now, there is still, obviously, things get complicated, because it's all good when you are accessing data, but when you execute some operations, that complicates the thing a little bit. For example, I make a fund transfer. The fund transfer is still handled by the core system. So there is no way that I can execute the fund transfer on my cache. What we do in this case, we still have to talk to the core system, unless we'll move out one day from the core system. And basically, even in this case, we have a normalizer that translates our global request into a country-specific, source system-specific request. Now, we just throw the request to the source system. All the state changes are coming back through our event pipeline. So we wanted this model to be as general as possible and as applicable as possible to any of our group in the bank. So basically, we came up with different components: Globalizer, Projector, and RPC server, which are fully configurable. So any group in the bank can basically take our components and build a service similar to this, adapting to a new core system, without writing any single line of code. For configuring the Globalizer, we use a custom DSL that we wrote. For the Projector and RPC server, even in this case, it's almost entirely configuration driven. We still have some challenges, of course. First one is that eventual consistency. Here we have built an entirely a system which is entirely eventually consistent. Now the problem is that your mobile app doesn't cater for eventual consistency. So whenever you do an operation and the mobile app triggers the read of any data, the update of the data might not have happened because there is a delay of throwing for the event to reach the database. Currently, we aim to keep this delay under 200 milliseconds, and this is one challenge. And the other challenge is that core systems are traditionally by nature batch oriented. So in some situation, they are not even able to send events for this kind of transaction. Like think about gyro transaction that happens in the middle of the night. So this requires us to build basically to refresh the cache after this operation happens. And to put it all together, this is basically an overview of the entire architecture. We are not there yet, but the whole idea is that in front of it, we're going to have a GraphQL layer which allows you from a single endpoint to query any domain of the bank. So from single endpoint, just like you do from when you interact with Facebook API, you just interact with one single GraphQL endpoint, and you're able to go to any of the RPC services. So that's about it. Thank you very much. And if you have a question, or in DBS we are always looking for talent. So if you're interested in joining us, just come to speak to me. Thank you very much.